Hello friends, welcome to EC Academy. In this lecture, let us understand a very important network theorem, which is Thevenin's theorem. Whenever there is a bigger circuit, every time we change the load across the terminals of the circuit, we have to redo the entire circuit analysis, which is very time consuming. That's why to simplify the calculation, we'll go with Thevenin's theorem. Thevenin's theorem states that any linear two-terminal network can be replaced by an equivalent voltage source in series with an equivalent resistance or impedance in AC. This simpler circuit behaves exactly same at the terminals, which means if we consider this circuit as an example, here if we want to connect different loads across the terminal 1 and 2, we need to redo the entire calculation for the circuit. That will be time consuming. That's why we can replace this complex circuit towards left side, which is known as active network, with a single voltage source and a single resistance that are connected in series between these two terminals. At that case, even if we change the load across these two terminals, the calculation will be easy or it is simple. So, Thevenin's theorem states that we can replace this complex circuit between two terminals by a single voltage source which is in series with this single resistance, which will behave same as this circuit between these two terminals. Now first let us understand the Thevenin's theorem for DC network. The left part of the circuit is known as active network. The terminal 1 and 2 are the output where we will connect different loads. Our main goal is to replace the left side of this circuit with Thevenin's source and Thevenin's resistance that is seen from terminal 1 and 2. To find the Thevenin's voltage or Thevenin's source and Thevenin's resistance, there are two important steps. First, we need to find the open circuit voltage VOC, which is nothing but Thevenin's voltage. Then we need to find the equivalent resistance R equivalent, which is RTH, which is Thevenin's resistance that is seen from the terminals with source equal to 0, which means we need to short circuit this source and we need to find the equivalent resistance. First, let us find the Thevenin's voltage, which is nothing but the open circuit voltage. Now we need to find the open circuit voltage between the terminals 1 and 2. So this voltage is nothing but the voltage that is appearing across the terminals of 10 ohm resistance. Since it is an open circuit, no current will flow through the 20 ohm resistance. That's why we can neglect this resistance and we can find VOC, that will be the voltage across the resistance 10 ohm. Now we can find VTH by using voltage division rule. The voltage division rule states that to find the voltage across any two terminal of a resistance, we need to take the resistance where we are finding the voltage divided by sum of the resistances multiplied by source voltage. So VTH will be equal to VOC, that is nothing but resistance where we are finding the voltage is 10 ohm divided by sum of the resistance is 10 ohm plus 5 ohm multiplied by source voltage, which is equal to 10. So this is equal to 100 divided by 15. So we can write VTH, which is equal to VOC, will be equal to 20 divided by 3. So this is the equivalent Thevenin's voltage. Now let us find the equivalent Thevenin's resistance, which is RTH, which is same as R equivalence. To find Thevenin's equivalent resistance in this circuit, we need to short circuit the voltage source. or we can make this voltage source as 0. If we short circuit this voltage source, there will be no voltage across this terminal. So from this circuit, we can write the equivalent resistance is 5 ohm parallel with 10 ohm, that will be in series with 20 ohm. So RTH, that is equal to R equivalence, will be equal to 5 ohm parallel with 10 ohm, which is 5 into 10 divided by 5 plus 10 plus 20 ohm. So why we have written this? Because 5 ohm and 10 ohm are in parallel, which is in series with 20 ohm resistance. Therefore, RTH, which is equal to R equivalence, will be equal to 70 divided by 3. So this is the Thevenin's resistance and this is the Thevenin's voltage which we found for this circuit. Now this active network can be replaced by this single voltage which is in series with a resistance, which will be having the value 20 by 3 as voltage source and 70 by 3 as the equivalent resistance. So this is the Thevenin's equivalent circuit for the active network of the given problem. Now this circuit is simplified and it is replaced by a single voltage source in series with single resistance. So this circuit will be having the same function as this active network. Now between these two terminals, the terminal 1 and 2, we can connect any load and we can do the simple calculations. Now let us use the Thevenin circuit to find load current. So general formula for load current is IL is equal to VTH divided by RTH plus RL. So here RL is the load resistance. Now for RL is equal to 30 ohm, we can find the load current I1 through this circuit. So this is the Thevenin's equivalent circuit for which we have connected a load resistance of 30 ohm, for which we need to find the load current I1. So we can find the load current I1 is equal to 20 by 3 divided by 70 by 3 plus 30. So if we simplify this, we will get I1 is equal to 0.125 amperes. Now let us find the load current for load resistance is equal to 20 ohm. So for this Thevenin's equivalent circuit, we have connected a load of 20 ohm. We need to find load current I2. So load current I2 can be calculated by taking 20 by 3 divided by 70 by 3 plus 20. So if we simplify this, we'll get I2 is equal to 0.1538 amperes. Similarly, we can find the load current for load resistance 10 ohm. For 10 ohm load resistance, we can find the load current I3 is equal to 20 by 3 divided by 70 by 3 plus 10. So this current will be equal to 0.2 amperes. From this, we understood that since we have simplified the complex circuit, by just changing the load, we can find the load current for the complex circuit. Since VTH and RTH is known, by changing the load, we can do simple calculation each time instead of reanalyzing the entire circuit. This is the advantage of Thevenin's theorem. This is about Thevenin's theorem and its application. Hope you have understood the topic. Thank you.